Hey class. So today we're doing the 6.2 and 6.3 review. And I'm going to start off talking about 6.3, which started off as more of a review of definitions and terms that you may have seen in classes previous, but this is kind of just a refresher on everything. So the first thing that we want to talk about is the definition of congruent. So when we say that two sides are congruent, we mean that they are the same length. And definitions like acute, obtuse, things of that nature, we have gone over in previous sections, so I don't feel the need to mention them here. But starting off with this first triangle, um, all the way in the top left, all of these angles here, they don't necessarily have to be the same measure, but they do have to all be less than pi over 2. And when this is the case, when all angles are less than pi over 2, we call this an acute triangle, because all angles are acute. In our second triangle here in the middle, we have one angle, theta, that is actually greater than pi over 2. And when this is the case, we call this obtuse. And here the thing to note is the acute triangle is the only triangle where we need 3 angles in order to name it. In both the obtuse triangle and the right triangle, which, by the way, this is a right triangle, I'm sure you know that, you only need one angle in order to classify it. So if you know one angle is greater than pi over 2, it's an obtuse triangle. And if you know one angle of a triangle is pi over 2 exactly, you know it's a right triangle. And that's how we classify. Um, these are classifications by angles. So when we talk about the side lengths of triangles, we can also classify them by which sides and how many sides are congruent. So when no sides are congruent, we call this a scalene triangle. When we have two sides that are congruent in a triangle, we call that an isosceles triangle. And when we have all three that are congruent, we call that an equilateral triangle. Is there two L's or one? There is one equilateral triangle. And again, this was just a basic overview just to go over this again. And now we'll move on to special right triangles. I lied. So before we get to the special right triangles, we have to first talk about similar triangles. So in chapter 6.3, we talked about the Pythagorean theorem for a brief period of time, and this taught us how to get lengths for sides of right triangles given some initial side or two. But when we don't have right angled triangles, we still have ways to get the side lengths. And if we compare two similar triangles, we can go through certain procedures to find out the lengths of each of these triangles. So similar triangles, the definition of it is in blue. And the definition of similar triangles is just triangles with similar shape, but not necessarily the same size. So I tried to draw two triangles off to the right of that, where we have one a little bit smaller than the other. But the similar triangles always are going to have these two properties. So these numbers are the properties of similar triangles. And the first property is that the corresponding angles have the same measure. And if you remember from when I was going over the names of triangles, I used tick marks to denote whether or not two sides had the same length. And we do the same thing for angles in similar triangles. So you'll see there's one angle with one tick mark, one angle with two, and that just means that those angles are the same measure. So for example, if the angle with one tick mark right here was something like 30 degrees, then that means automatically this angle right here is also 30 degrees. And that's good because that sets up the second property. And the second property is that the ratio of lengths of any two sides of one triangle is equal to the ratio of lengths of the two corresponding sides of the other triangle. So it's a lot of words to say that if we take the ratio A over C, so that's this side over this side, that is going to be the same thing as X over z. So the same lengths, the same corresponding lengths, but of the different triangle. And this will always be the case with similar triangles. So even if we can't use Pythagorean's theorem, we can still use this second property of similar triangles to try to find the lengths of sides. So from here, now we would go on to special right triangles. Okay, so here we finally arrive at special right triangles. And alongside special right triangles, we're going to be mentioning trig functions. So off to the left, we have all of the trig functions that we defined and introduced in this section. And again, we have the rule SOHCAHTOA, which allows us to remember sine, cosine, and tangent. So sine is always going to be opposite over hypotenuse, cosine adjacent over hypotenuse, and so on. Cosecant, secant, and cotan can be remembered through just memorization, or you can remember the inverse relations. But either way, you should be able to recall those. So when we talk about special right triangles, we have two special right triangles. First is going to be the pi over 6, or the 30, 60, 90 triangle, as you may know it. And then we have the pi over 4 triangle with, or the 45, 45, 90 triangle. So using these special triangles, we can create a chart and use this as kind of like a cheat sheet to remember what the values of sine, cosine, and tangent are given either a 30-degree angle, 45-degree angle, or a 60-degree angle. Right? So when we create this chart, we're going to reference those diagrams that I have above. Right? So the pi over 6 sine of 30, opposite over adjacent for 30. 30 is a pi over 6, so opposite is a, hypotenuse is, oh, is that supposed to be a square root too? No, that's fine. So this is 1/2. And continuing to use this logic, we see that sine of pi over 4 is 1 over square root 2. And sine of pi over 3 is square root 3 over 2. For cosine, we're going to have cosine of pi over 6 is square root 3 over 2. Cosine of pi over 4 is 1 over square root 2 as well. And cosine of pi over 3 is going to be 1/2. For tangent, we are going to have 1 over square root 3 for pi over 6. We're going to have 1 for pi over 4. And we're going to have square root 3 for pi over 3. And again, you can kind of use this as a cheat sheet or a reference to try to recall all of these known values for sine, cosine, and tangent given these special right triangle angles. So if we were to look at an example like cosecant pi over 6 plus cotangent of pi over 4, excuse me, we can evaluate this using the cheat sheet that we just created. So cosecant of pi over 6 is hypotenuse over opposite, which if you look closely is the inverse of sine. So that means that cosecant pi over 6 is going to be 1 over whatever sine of pi over 6 is, and that just happens to be right here. So this is going to be 1 over 1/2, and cotangent of pi over 4 is going to be the inverse of tangent, because if we look at cotangent, that's going to be the inverse of tangent. So if we look at tangent pi over 4, that's going to be 1 right here. And so cotangent pi over 4 is just 1. And simplifying this fraction by multiplying by the reciprocal, which is just 2, we get 3. So we can use this chart while we do examples like this. So whenever we're dealing with trig functions and we don't have an angle of pi over 3, pi over 4, and pi over 6, we can still evaluate those or simplify the expression by using identities. Identities just help us rewrite expressions in simpler terms. So like I explained in class today, it's kind of like just, if we say x squared plus 3x squared plus 4 minus 6 equals 12 and stuff like that. in algebra, you would simplify this expression by adding like terms. Similarly, we're going to use trig functions to simplify our trig expressions. And the identities that we are going to use, the first one is called the quotient identity. So the quotient identity. Why is it called a quotient identity? Well, it's because it is a quotient. Simple enough. So tan theta, if we look here, is opposite over adjacent. And we can create an opposite over adjacent fraction by taking the fraction of sine over cosine. So that's going to be one of our quotient identities. The second is going to be for cotan. And you can see that, again, because cotan is just tangent flipped, right? Instead of opposite over adjacent, it's adjacent over opposite. We can just flip the right-hand side of that tangent identity to get cotangent. Okay. The second identities that we use are the reciprocal identities. And the reciprocal identities are called reciprocals because they are, in fact, reciprocals. So again, I use this in the example with the chart. Sine theta is opposite over hypotenuse. And if we flip that fraction, we get hypotenuse over opposite, which just so happens to be cosecant. So we can write sine theta as 1 over cosecant theta. Similarly, we can do the same for cosine and secant, and tangent and cotangent. So we have cosine theta is equal to 1 over secant theta, and tan theta is equal to 1 over cotangent theta. So again, these are two categories of identities that we can use to simplify expressions, and they're extremely easy to prove. If you ever get confused, just look at the trig functions and their definitions using the side lengths of a triangle. Again, so if you flip opposite and hypotenuse here, you get a different function, and that just so happens that you get the secant function, or sorry, cosecant function, hypotenuse over opposite. So we have one more category of identities to talk about, which are the Pythagorean identities, and then we have, we also have cofunction identities to talk about, and then that's it for this video. Okay, so the next set of identities we can talk about is the Pythagorean identities. And I just want to go through the derivation super quickly to remind you guys how we got these. So if we write a squared plus b squared is equal to c squared, I know you guys recognize this as a Pythagorean theorem. But when we have a right angle like this, and we just have some theta, we label these sides instead of A, B, and C, we label them as opposite, adjacent, and hypotenuse. So if we replace A, B, and C with adjacent, hypotenuse, and opposite, we get something like A squared plus O squared is equal to H squared. This is just an expression, right? This is always going to be true for a right angle triangle. So just like any other expression, whether it's x squared plus 8 or, y equals x plus 2, we can move things around and adjust it and still get a similar or equivalent equation or expression. And the first thing we can do is just divide everything by h squared. So if we divide both sides of this equation by h squared, what do we have? So if we divide this by h squared, right here, we're going to have a term that is adjacent over hypotenuse squared. Well, we have right here that adjacent over hypotenuse is called cosine theta. But then we can replace that with cosine squared theta. Similarly, we have opposite over hypotenuse here, but we have that sine theta is opposite over hypotenuse here. So we can replace this with sine squared theta. And then we have h squared divided by h squared, which is just 1. So this is called a Pythagorean identity because it is always true, and we derive it from the Pythagorean theorem. There are two other Pythagorean identities, and they stem from dividing by a, so dividing both sides by a squared, and the other Pythagorean identity comes from dividing by o squared. And just writing those really quickly, or opposite squared, we get, I think it's cosecant squared theta. No, it's secant squared. Sorry. When we divide by a squared, we get secant squared theta plus 1 is equal to hypotenuse over, was it a squared? Okay, I messed this up. Okay, I figured it out. So if you divide by a squared, on the left-hand side, you're left with opposite over adjacent squared, which is just tan squared, and you get adjacent over adjacent, which is just 1. So you get tan squared plus 1 on the left-hand side, and on the right-hand side, you get secant. And then when you divide by o squared, you're left with cotan squared theta plus 1 on the left hand, and cosecant squared on the right-hand side. Okay, so last thing we're going to talk about really quickly is going to be the cofunction identities. So here's the last topic we're going to talk about, and I do want to go into a tiny bit of a derivation so that hopefully this gives some clarification as to why we're learning about cofunctions and why they have the formulas they do. So first, remember that when we talk about complementary angles, we're talking about angles that sum up to 90 degrees. So right here up in the upper right corner, I've drawn just an XY axis, so you can think of this as the positive Y axis, and this line as the positive X axis. And what I've drawn is just a random set of triangles, right? So I started off by drawing this red ray right here, which is going to be the hypotenuse of both triangles. And then I made a right angle with each axis. So if we look at theta 1 and theta 2 and try to talk about their sine and cosine values, right? Well, we can call this distance on the x-axis, we can call that the opposite of theta 2, but it's also going to be the adjacent of theta 1. And similarly, we can look at the y-axis distance right here that I've drawn, and we can say that this is going to be opposite of theta 1, but it's going to be adjacent to theta 2. So maybe you've already made the connection, but if we look at the sine value of theta 2, and so let's look at sine of theta 2. So sine of theta 2, actually it's better to do tangent. So if we look at tangent of theta 2, this is going to be equal to the red A, or sorry, opposite over adjacent. So the green O and the red A. So over A. Now, since since the green A is the same as the green O, we can simply change this to adjacent. And since the red A is the same as the red O, we can change this to opposite. And we can see that if we look at theta 1 now, the green A is adjacent and the red O is opposite. So we've actually just determined cotangent of theta 1. But here's the thing, theta 1 and theta 2 are complementary. So what I've just derived is that tan of theta 2 is equal to cotangent of 90 degrees minus theta 2. How do I do that? I used the definition of complementary angles. Since theta 1 plus theta 2 is equal to 90. Then we can subtract both sides by theta 2, and we find that theta 1 is equal to 90 degrees minus theta 2. And then I just plugged this value for theta 1 into here. And now I've shown why cofunctions have the definitions they do. It's because when you have complementary angles, you can make right-angled triangles with those two angles. I may have mixed that up. So when you have complementary angles, you can draw an x and y axis like I did here. And you can create right angles by simply drawing a straight line right here. And then what happens is the opposite of one angle will be the adjacent of the other. And same, the opposite of the, okay, so the opposite of each angle will be the adjacent of the other angle. So this is how we get the definitions of all the cofunctions. And this stays the same for sine theta is equal to cosine of 90 minus theta, and secant theta is equal to cosecant of 90 minus theta. And with that, that is everything that we covered in both 6.3 and 6.4. So I hope this clarified things for you guys. I hope you enjoyed it, and I'll see you next time.